Let's begin. Hi, everyone. I feel like you're all so anxious about exam one and wanting a lot more information. Made me doubt about my ability to explain and clarify things. And so maybe there's some of that. But also make sure you read the announcements and make sure you have your alerts turned on. Like last week, there was confusion about whether you can use Jupyter Notebook or Python, but I had specified that you can use Python. If you want to put it in a Jupyter Notebook, that's fine. But I think what wasn't clear is whether you're allowed to use your homework assignments or notes. No, you cannot use any of those in the exam. The only thing you can use is what I allow you to use, which is your cheat sheet, double-sided letter size, legible font. You don't have to use a magnifier. If you need to use a magnifier to use your to read your cheat sheet, then you've used a very small font size. Okay. In addition to that, you are allowed to use the generic script that we created last week, which I shared yesterday, and I was going to put on the front page as well for those who didn't attend the lecture last week. Sorry about that. But it's there. You're welcome to use that. And today I'll work through about 25 examples on all sorts of different probability distributions. You'll get an idea of what the questions will look like. It's, in my opinion, it's a very, very easy exam. This type of exam, it's a lot of low stakes questions. Many have been wondering what kind of derivation, what kind of notation was used. You're not going to need any of that, because these questions are tops 1 minute, 1.5 minutes long. They're low stakes, quick answer. There's like 44 questions of them, 40 questions, right? And I've done that over the years. It works really well. Maybe you're not used to that, but it's not as scary as you might imagine. Okay, let me go back to the home page. So yesterday I also sent an announcement clarifying a few more things on the exam. You're allowed to use your calculator. You're allowed to use built-in functions, your calculator, Python, Jupyter, Excel sheets. And if you're choosing to go with Google Sheets or Excel sheets, and you have a pre-made Excel or Google Sheet calculator, you are allowed to use that. That's okay. All right. That's like programming some built-in functions in your calculator. That's okay. Even if you have your own like Jupyter script that you've created, okay, that's okay. But I'm giving you everything in Python today and from that generic script. So I'd rather use that so nobody feels disadvantaged in one way or another, or at least you use tools that are vetted by Professor Saad. So, we'll make sure of that. I think the scripts we will work through today and the one we did last week is sufficient for all the problem questions. The questions are low stakes. There are no lengthy derivations, nor complicated lengthy questions. They're either yes, no, true, false, but they're going to make you think. Right? If I ask you about the dimensions of this variance versus the standard deviation, or some high order moment, right? Takes you a minute to think about that, but that means you need to know your definitions very well. And the equations, put them on your note sheet. They're finite. Standard deviation, variance, mean value for discrete, same for continuous, and for continuous you have the extra stuff for expected value. That's pretty much it in terms of equations. But then I'll ask you a question about that. You go into a little bit of deep thinking about it. You might need to scribble something on your scratch paper. That's absolutely, you should do that. That's fine. But that's it. You have either multiple choice or a numerical answer, true or false, yes or no. That's it. That's literally it, okay? So, yep, that's explained here. So my advice for studying is know your definitions very well, okay? Know the definitions very well. Questions look like this, like a shipment of 100, very short questions, contains 15 faulty ones. If 10 are tested, what's the probability that at most one is faulty? Okay, that immediately jumps hypergeometric. Open up your notebook or your calculator, put in the numbers, get the answer, put the answer. Can you define a mean value for categorical data? Yes or no? Compute the standard deviation for the following set. like 4 numbers tops, right? You can punch that into your calculator or do it by hand, okay? Or put it in Python, that's fine, just get the answer. Which of the following best describes theoretical probability? You have like 4 answers, select one. Those are the types of questions, okay? So you need to know your definitions. It's nothing outside what we discussed in the lectures, okay? In the slides, it's all in there. All right, now I'm not even referring to the textbook. The textbook has material that we did not cover or that we covered in different order. So you're not responsible for material we didn't cover. This is like I'm giving a lot about, you know, exams are supposed to have this mysterious component, so to make you all on edge. But you know, I'm happy to give you what so far what I have: 6 questions on descriptive statistics, 2 points each, 3 questions on general probability. That's essentially you look at the sample space, like you flip a coin 3 times, what's the probability of getting 2 heads in a row? Okay, you look at the sample space, divide, get the number, right? There's only 3 questions on that. Each is worth 1 point. Okay, so now don't go and say, oh, I'm only going to be asked for 3 points on the exam. I'm not going to study probability. Because this might change a little bit. I reserve that right, but that's in general my intent. It's not going to be heavy on probability. Okay, this could go up to 5 point stops maybe. I don't think so, but discrete distributions, general discrete distributions, 5 questions. Binomial distribution, 3 questions. So those are numerical questions. Okay, this is look at where most of the points are. 3 points per question on binomial hypergeometric Poisson, so 9 questions. Uniform and normal distributions, also 6 questions and 3 points per question. So those are where you're going to do calculations like probability, CDF, PMF, etc. Okay, but then I have some generic questions about discrete distributions and generic questions about continuous distributions. Okay, so this would be the PDF and CDF. This would be PMF and the CDF as well, but generic questions on those. And I did the Q&A from this year. I posted that earlier this morning. So you can look at that. If we have time later today, we'll look at it. There's about, I didn't count the questions, but there's how many pages? 6 pages of questions. Those are going to be a great study guide for you. Many of the questions were on just clarification about the exam, and I wish you used this opportunity for Q&A to ask actual technical specific questions, because clarification questions, you know, you can just come and ask me, or I'm going to discuss about that in the class or in the front page, right? There are a few very specific questions, right? Like you see, like the questions were generally like, what's the format of the questions, or what proportion questions will we have on the exam? Well, that's kind of, those are not the intent of the Q&A. When I do the Q&A, I want you to ask specific questions on topics you didn't understand. And so, you know, I did answer. I normally just eliminate the questions that are non-specific, but we'll discuss this. We'll discuss this if we have time later. But that's the Q&A. You should go through it. There's a Q&A from 2025. There are questions from 2025 that are not relevant to this year. So dismiss those questions, okay? Because we covered topics like nominal data, ordinal data, and some other stuff. You're not responsible for that. So don't freak out if you see a question in 2025 doesn't apply this year, okay? In addition, I added some, the documents, the PDF, I noticed that many of you do not use the resources that are under files. There's a ton of reading material, a treasure trove of problems and assignments that I choose from, I modify for exams, for examples, for homework. There's a ton of those in there, and I know that I can see kind of the activity on who's accessing what and how often they're being accessed. They're underused. Only 25% of you are looking at what's under the reading. So if you go specifically under files reading, there's a ton of material in there. I link to them here. those are chapters from 2 textbooks, Beginning Statistics, chapters 5 and 6, and Miller's textbook, Statistics and Probability for Engineers, chapters 4 and 5. They have a lot of the discussion. I base my learning and my slides off of some of the material in there. But like if you look at this chapter, for example, it's really high quality PDF, talks about genetically probability distributions, random variables, and then, you know, gives you a different perspective of things. You go, if you know, like we did this in class, right? Remember the CDFs, etc. Now it's using it's using R or a different calculus software. We don't need to worry about that. But it talks about the distributions. It has a ton of examples. And if you want to practice problems, look at that. There's a ton of exercises, okay, that you can work through. And so, you know, I thought everybody would be using those. But when I checked today, I was like only 25%. So I also don't mean to, I mean, this could be overwhelming. I'm not asking you to go study these. But if you want some, you know, some extra exercises to work through, you can pick from these textbooks if you want. What's really cool about these chapters as well, if you go to the end, so this one, there's like a study guide, okay, which many of you find useful. Some of you like to do their own study guides. So in this one, they call it do's and don'ts. So it just goes through a summary of discrete distributions. That's what we did. Binomial, hypergeometric, and then Poisson distribution, right? And if you go back, if you go to the other one, beginning statistics, if you go to this chapter, Chapter 5, discrete distributions. This is not as high resolution as the other one because I scanned it. But if you go to the end, this is a little bit more elementary in its discussions, but still it's fairly useful. Okay, look at that. They have what's called a review section, Chapter 5 review, discrete random variable, right? Properties, etc. Goes through all the details and explains things to you, but it doesn't have the tables yet. So you know, this might be helpful for you if you wanna look at that. I personally like to design my own. If I were studying, I like to design my own study guide. But for those who asked, you know, you could use these resources. I post a lot of stuff in the reading material. Please check that out. You don't wait for me to assign that to you specifically. So either screenshot from my slides and put them in your cheat sheet, or study from this if you want, okay? But again, going through the examples in the slides, etc., it's not going to be any different than that, okay? So before I open the floor for questions, I want to go through a series of examples together just as a review, all right? And this will give you an idea of how the questions are going to look like. You're going to be, if you're not bored by problem number 10, you'll be bored by problem 15, okay? Because it's just the same thing over and over again, all right? So open up a new Jupyter notebook, and you can type with me, and I will share. And if you don't type, I think you should type with me so you can work out the examples yourselves. But I will be sharing these notebooks as well on Canvas. All right. Let me turn back. And so the notebooks are going to look like this. So that's what I will share with you on Canvas when we're done here. But this one has, I have 5 notebooks for each of the key distributions we worked with: binomial, hypergeometric, Poisson, uniform, and normal distribution, okay? So 5 notebooks. Each notebook has 5 examples, looking at probability to the left, to the right, in between, and the tails, greater than, less than, or equal, etc. Okay? So, and it has these summaries at the beginning. So I will share this with you. But and I'll work through one example at a time. All right, so I'll move this here. Let's say we're starting a new notebook, and from scipy.stats, import binomial distribution. And then the first problem we will be looking at, if I can see this right here. Okay, so the first problem is the following problem. Let me zoom in a little bit here for those in the back. There was a nice view. I'll just zoom in. A factory produces microchips with a 2% defect rate in a batch. Once you see a percentage, a probability of failure or success given to you, that should immediately ring a bell that this is a binomial distribution. Because compared to the hypergeometric distribution, I could tell you I have a factory produced 100 microchips and 2 of them were defective. What's the probability that in a batch of 50 chips, exactly 3 are found defective? This problem I just stated should be hypergeometric because I'm giving you the total number, numerically, the total number of items, the population, and the number of successes in the population or failures in the population. That should mean hypergeometric, but you can also treat that as a binomial. You shouldn't, except under certain limits, but you shouldn't treat it as a binomial. But once you see, instead of giving you the population and the success rate, instead of that, I just give you the success rate as a rate, as a percentage, okay, that should scream binomial. Binomial distribution only has 3 parameters: P, the probability of success or failure, the number of trials, 50 chips, and the probability of the item, exactly 3 are found defective or not. So what you should do on your scratch paper is say, well, okay, what they're looking for, this should be binomial distribution, and I'm looking at P exactly X equal 3, okay? So in this case, I'm going to do N is equal to 50, and then my P is equal 2%. You can, if you forgot how to do 0.02, you just do P is equal to 2%, and your X is equal 3, and then you call binom. Now, I expect many were asking, are we going to be doing coding or Python questions? No, but you should know how to use the binom distribution if you're using Python to put your answers, okay? If you're using your calculator, I don't know what calculator you're using. You better know how your calculator is doing binomial distribution. If you're using Excel, you better know what Excel is doing, okay? But I will not ask you, like, what is the syntax of using binom? This is a silly question. I wouldn't ask that, okay? So we're looking at the binomial distribution, and we're going to do the PMF in this case because this is exactly at X equal 3. So binom.pmf, and we want at the X value, which is 3, and then NP, okay? And that gives you 6% chance of exactly 3 being defective found in a batch of 50. Okay? This is a typical exam question. You might have to do a numerical answer or choose from 4 or 5 answers. I will give you the numerical value, choose the one. If you're typing in a numerical answer, just put 3 significant figures. The answer is within a range, so it will catch it if you're correctly within range, okay? So I would put 0.060, for example, in this case. Okay, question 2. All right, so let me copy this. A communication channel has a 1% bit error rate. So if 100 bits are transmitted, what is the probability that 3 or more bits are erroneous? Again, you have 100 trials asking the 3 or more are erroneous. You have the success or failure rate. In this case, P is 1%. This screams binomial from a mile away. Okay? So what would it be here? I always would write it as a probability. So this should be binomial. And my probability that 3 or more, so that's x greater than or equal to 3. Okay? Because that's 3 or more. If I had asked more than 3, it would be x greater than 3. Okay? So n is 100, p is 1%, and then x is equal to 3. And then what I'm doing here, I need to use the CDF, and that's 1 minus binom dot CDF, and I give it x. Actually, I'm going to give it, so because we want x 3 and higher, so we want this at 2, okay, because we're doing the CDF. So x and p. Okay, is this clear? Because we're looking at the probability from x equal 3 and higher inclusive. So we're going to do 1 minus the CDF until 2. Because the CDF until 2 includes 2, doesn't include 3. So draw the diagram, etc. Okay. Let's do one more on binomial. Each bolt in a factory of bolts, has a 5% probability of failing a stress test. Out of 20 bolts tested, what's the probability that 2 or more bolts fail the stress test? So again, this is similar to the previous one. That's a greater than or equal probability. Let's actually do an interval question. Let's do this one. So this screams binomial, and then we want p of x greater than or equal to 2. Okay? And then my n is equal 20 bolts, p is equal 5%, and then my x is going to be equal to 1 because I'm doing 1 minus binom dot CDF, x and p. Okay? That will give you 26.4%. Now, your answers in Canvas are not percentages, right? Unless I tell you, report your answer as a percentage. Don't put percentages. Put the fraction, okay? The 0.26. All right, so let's do this one. Each sensor works correctly with a probability of 0.9. In a system of 15 sensors, what is the probability that 12, 13, or 14 sensors are correct? So you can do this in a number of ways. You can either add the PMF of 12, 13, or 14 because you're, yes?
In what case would we use like 1 minus binom dot PMF instead of CPF? Would you ever do that?
There's no situation where you have to do that because the PMF is a value only. The PMF is a probability at a singular value. The CDF gives you the area. So 1 minus PMF is essentially giving you the area, all the probabilities outside that point. So in other words, the only case you might use, let's say, what is the probability of not getting a 3? It's 1 minus binom dot PMF 3, right? So it gives you everything except 3. Okay, that's the only case where I would see this happen. It's an interesting question. I hadn't thought of that. Yeah. Good exam question. Thank you very much. Okay, prepare for tomorrow. Okay, so this one, you can add them up together. Okay, you can add them up together, or you could do, the CDF at 14 minus the CDF at 11. Okay, either one of those should be fine. And we can verify this answer. So this should be binomial distribution, and we're asking for x between 12 and 14 inclusive, okay? So my n is 15, my p is 0.9, and I'm not going to put a and b here for now. So I will do binom dot, actually, let me put A is equal 12, B is equal 14, and then I do binom dot CDF of B, right, and P minus binom dot CDF A minus 1 unless A is 11 over here. Okay, then you could do A and P. And that should be equal to the sum of the individual PMFs. Binom.PMF of 12 NP plus binom.PMF of 13 NP plus binom.PMF at 14 NP. Okay? It's exactly the same answer. Okay? All right. Let's do one more, and then we'll skip a few on the other probabilities because I want to do an open interval example. Each packet is transmitted successfully with a probability of 0.95 out of 30 packets. So this is like internet data. Out of 30 packets, what's the probability that more than 25, so more than 25, not 25 and more than 25, I put in parentheses exclusive, and less than 30 instead of 30 or less. Okay? If I said 30 or less, it will be inclusive. If I said less than 30, it's exclusive. So you're not going to see those parentheses exclusive, inclusive in the exam. You have to work with the nomenclature we use in class. So more than 25 and less than 30 packets are transmitted successfully. So again, this is binomial. I have 30 trials, 30 packets. I have a success rate of 95%. And then what's the probability that more than 25, so X is between 25 and 30 exclusive. Okay, so this is binomial. And then I'm looking at P of 25, so X between 25 and 30. And N is 30. 30, P is 0.95. And then I can do binom.CDF of 30, okay, 29, because less than 30, so 29 NP minus binom.CDF. We said we want to be greater than 25, so this would be so we would take out the area including that 25. Okay, so 25 NP. So if you were to draw like these bar graphs, this would take out the area from 0 to bar 25. So we don't include the probability of 25 because it's exclusive, all the way to the probability of 29. We're including 29, but we're not including 30. Okay, so that's the open interval. All right. Okay. Okay, so next we will do some hypergeometric examples. Yeah. Uh-huh. Yeah, the binomial is a discrete distribution. Only works for discrete values. Yep. Not sample size. It's the trials. They're called the trials. Yep. Yeah, I mean, it's a sample, really. We're going to sample, but from the binomial language, if I tell you, in 30 trials, what that means is I'm picking up 30 objects, right? Yeah. I mean, it's a sample, but in the lingo of like when you go and let's say you're pulling your calculator or Excel, they might tell you, oh, this is the number of trials. And you're like, sample, trials. Yeah, the lingo for the binomial distribution is trials. All right, so I'll continue with this notebook. Now, if you remember, the hypergeometric distribution was the Python nomenclature was a little awkward, didn't look exactly like the nomenclature we did in the slides, but then I had a slide explaining what you need to know in the how to put in the numbers in the hypergeometric distribution. So essentially, the hypergeometric distribution is like a binomial distribution, but without replacement. And one other thing with the hypergeometric distribution problems is you are given the total population. So I tell you, I have a class of 50 students, and 5 of them wear hats or something, right? And so that immediately screams hypergeometric, okay? Versus saying 2% of my class wears hats. I didn't give you the population. I didn't give you the number of people wearing hats, but I gave you a probability of hat-wearing persons. So that would be binomial, okay? So with the hypergeometric, you have 4 parameters: the population size, the number of successes in the population. So that's a number, not a rate. The sample size drawn, but without replacement. So we're picking a sample, asking a question on that. And X, the number of successes in the sample. You're asking the question, if I have K successes in the population, what's the probability of getting X successes in the sample? Okay? So I hope you know this very well by now. If that you've been studying over the weekend. Of course, you've all been studying over the weekend. Guys, you remind me of myself. Okay, a batch contains 40 components, 6 are defective. A batch of something, whatever. You dream of what you want to put in this batch. If 8 are inspected without replacement, what's the probability that exactly 2 are defective? Classic hypergeometric problem. Your population has 40 components. K, so that would be capital N. K is the number of successes in the population. That's equal to 6. So I know they're defective, but that's what we're going to call success. Lowercase n is my sample size. So make sure you understand, you remember this nomenclature for Python. X, capital N, capital K, lowercase n. Okay? Number of successes in the sample, population size, successes in population, sample size. If 8 are inspected, that's lowercase n, without replacement, what's the probability that exactly 2 are defective? All right, so you would just put in, so I would do hypergeometric, and like I recommend you do, you should turn this into a probability problem, P of x equal 2. Okay, that's the probability question. So this is going to be a PMF question. And I would put n equal 40. Okay, so again, you're welcome to use this notebook. I will give you this notebook with all of this explanation. So you're welcome to just use that. K is equal to 6, number of successes in the population. N, 8 are inspected, and X is equal to 2. And this is, I need to import the hypergeometric distribution. So from scipy.stats, import hypergeom, right? And then I can call hypergeometric.pmf, and the format is xnkn. So xnkn. That gives me 26.23%. Okay? And then it repeats. Same thing, same thing. A shipment of 100 sensors contains 15 faulty ones. Again, this immediately screams hypergeometric. I have a population. I have I'm given the number of successes in the population. If 10 are tested, that's my sample. What's the probability that at most, 1 is faulty? So 0 can be faulty, or 1 can be faulty. So this is P, probability of x less than or equal to 1. So again, I would say this is hypergeometric. Geometric, P of x less than or equal to 1. That would be a CDF. Okay, and then I would do n is equal 100. K is equal 15, put capital K to stay truthful to the nomenclature. N is equal 10. And I'm not going to put x because we're just going to build it together. This would be a hypergeometric dot CDF, okay, because we're x less than or equal to 1, and that would be hypergeometric at 1. I guess I can put x here. 1, and then n, k, and lowercase n, right? So that gives me the probability. So this would be equal to the hypergeometric PMF at 0 and 1, plus 1, you know. I think what you're going to be entangled with is intervals. Oh, what should I do? Put 2 or 3, Sarah, right? Okay. A lot of 30 circuit boards contains 5 defective. 6 boards are selected. What's the probability that at least 2 are defective? Okay, at least 2 are defective. So this would be a hypergeometric distribution with hypergeom, with 30 population. K number of successes is 5. 6 boards, that's my sample, n, or the trials, the number of trials. And then what's the probability that at least 2 are defective? At least 2. So in other words, 2 or more are defective, right? So at least 2, it means 3 can be 2 can be defective, 3 can be defective, 4. So that's the probability of x greater than or equal to 2. Okay? At least. Okay? The previous problem was at most. So this would be P of x greater than or equal to 2. Okay? All right, so let's do this. N is equal 30. K is equal, capital K is equal to 5. N is equal to 6. And I'm going to put my, and this is going to be a CDF, okay? 1 minus hypergeom dot CDF. Okay, I'm going to leave the x open for you to think about it. Okay, what should be the value here? So we want the area to the right of 2, including 2. So we're going to take 1 minus, minus the area to the left of 2, which includes 0 and 1. So that would be 1 minus CDF at 1. Okay. A warehouse has 80 steel rods, 12 are cracked, hypergeometric. If 15 rods are randomly selected, all you have to do is like, yes.
I have a quick question.
Yes.
Does replacement matter with these questions?
It should be without replacement. Now, I'm not specifying that. I'm not specifying that. So you could have modeled this as a binomial distribution. How would you do it? With the binomial, you need the probability of success. So how do you calculate that? If you remember, there was a slide where I said, okay, the hypergeometric can be modeled as a binomial. So how do you get the probability of success? In this case, 5 over 30, right? So you could do this as a binomial. In fact, let's try it out. Let's try it out. Let's say, let's assume we model this as a binomial. With the binomial, you don't have concept of population, but you have just the sample, which is 6, and the probability, which is going to be k over n. Agreed? That's the number of successes divided by the population. That's the likelihood of getting the item, the defective board, right? And then I'm going to do 1 minus binom.cdf at 1 and p. Okay? 1 and p. And it's going to be pretty darn close. 0.254, 0.263. Okay. Now, as n becomes larger, it gets closer to the binomial. But I didn't say here with or without replacement. The assumption is that they're without replacement because you're just kind of picking. Yeah, because I'm asking, what's the probability that at least 2 are defective? It's not I'm going to pick one, see it's defective, and put it back, and then pull another one, right? So what's the probability? So it's inherently no replacement. Now, as the population size gets larger, okay, this will approach a binomial distribution. With or without replacement, it will not matter. Good point. Thank you. So a warehouse has 80 steel rods, 12 are cracked, 15 rods are randomly selected, so we're just going to select them. We're not going to put them back. What's the probability that between 2 and 4 inclusive are cracked? So that's as clear as day. So hypergeometric, and then P is between 2 exactly inclusive and 4. Okay, N is 80, K is 12, lowercase n is 15, and then this is a in inclusive interval. So the first one is going to be the area to the left of 4. So hypergeom dot CDF of 4 and then n k n. Okay, so that gives me the area to the left of 4 including 4. Next, I need to subtract the area to the left of 2 excluding 2. So it would be a hypergeom CDF at 1. Right? Gives me, I'm not going to say 6, 7. So I showed my oh darn it. I showed my kids the clip last time where the answer was 6, 7, and they loved me for like a week. Okay. You know what they tell me? They tell them like, Poppy, what are you doing? You know, come play with us. I'm like, no, I'm making an exam for my students. They come. Are you gonna make it hard? It's like, yeah, I'm gonna make it. It's like, yeah, make it hard. Because I complain. There's a chain of complaining because I complain about their teachers giving them hard homework. So I have to give someone hard exams. And then you go and give someone else a hard time or something, right? It's a chain. It's the cycle of screaming, of making things difficult. Okay. A shipment of 60 batteries contains 8 defective units. So again, screams hypergeometric. If 12 batteries are tested, what's the probability that more than 3 are defective? So what do you think? Hypergeom. Okay, more than 3, P x greater than 3. Okay, so hypergeom, P x greater than 3. Okay, so all of these questions are typed up for you. You're gonna get them. I'll just post everything on Canvas. Okay, so if you want, just focus on typing the code, just to practice it in extra time. So n equals 60 and k is equal 8. 12 batteries are tested. That's the sample. And then I need P of x greater than 3. So that's going to be hypergeom dot CDF. Okay, I'm going to put the x first. N, k, n. Okay, so we want the probability greater than 3. So so 4, 5, 6, and more. Okay, think of it this way if it's easier. That's 1 minus the area to the left of 3, including 3. Because P of x greater than 3, I want to include 4, 5, 6, P equal 4 plus P equal 5 plus P equal 6, and so on, not including 3. The CDF at 3 gives me the area to the left of 3, including 3. So there's a 95% chance that more than 3 are defective. Okay. Next, we will do the, oh, my apologies. Yes, sorry. Thank you. I'm thinking like 95, that's too high. Like everything is, they should shut down the factory with like, red wax and like nobody approaches this factory. Okay, thank you.
You go up to it, it's just like, oh boy, what is that?
I love abandoned places. They're like the quietest places ever, and you see how nature takes over. There was a show called Life After People on History Channel or Discovery Channel. Fun show if you like that weird stuff. Okay, the the fish distribution. Yes, the fish distribution, the Mr. Poisson. So Poisson, it's an interval over time, okay, and formula, etc., all in the slides. But for Python, PMF, CDF is just K and lambda, okay. Now, the average rate that's usually given to you, or you might have to compute it over time, that would be lambda, and then K is the number of like events occurring in that that you're testing for, okay. So that's like the number of trials, if you want, or the success rate, whatever you're trying to measure. So from scipy.stats import Poisson. Okay, we do a bunch of problems. A server experiences an average of 4 failures per week. So we're given lambda. What is the probability that exactly 6 failures occur next week? All right, Poisson distribution. It's a model. We're modeling this process with a Poisson distribution. With absence of any other info, this is the best we can do. So we need to compute P of x equals 6. And then this would be, so lambda is equal to 4, right? And my k, or my x, or k, this should be called x. Actually, let me call this, let me call this x over here. Okay. All right. And then my x is 6. And then Poisson dot PMF x lambda. 10%, 10.5%. All right. Are you bored yet? No? Darn it. So we are at problem 11 now. And an engineering help desk receives an average of 10 requests per hour. What is the probability that at most, so you have less than, 8 requests arrive in the next hour? So I'm going to model this. So I have my average requests per hour, and they're asking 8 requests for the next hour. So I'm going to do Poisson and probability that at most 8 requests. So 8 is inclusive, x less than 8. And then my lambda is equal to 10. And then my x is equal to 8. And then this would be Poisson dot CDF of x lambda, right? So I'm taking the area to the left of 8, including 8. Okay, Poisson of 0, 1, plus 1, plus Poisson 2, plus Poisson 3, 4, 5, 6, 7, 8. All of those, that's what the CDF gives you. Okay, 33.3%. A production line averages 2 defects per 100 meters of cable. Okay, what is the probability that more than 3 defects occur in the next 100 meters? Okay. Now, make sure that your lambda is the average over the same unit you're using here. Okay. If we were asking what's the more than 3 defects in the next 50 meters, then you need to compute lambda over the next 50 meters, okay, which approximately would be lambda over 2 in this case. Okay? So just watch out. That's the only trick I can think of, one of the few tricks I can think of for this problem. What is the probability that more than 3 defects occur in the next 100 meters? So this would be Poisson. And then more than 3 defects, so we want P x strictly greater than 3. And we have our lambda equal, what is it? 2 defects per 100 meters. And then we want probably x of greater than 3. So that would be 1 minus Poisson dot CDF. So greater than 3, we want to include 3 in the area to the left, and then lambda, right? So greater than 3, we want the area of Poisson equal 4, 5, 6, 7, 8. So that means that's 1 minus Poisson 0, 1, 2, 3. Okay, so that would be CDF at 3. Initially, I started out by writing a script like the one we did for continuous distributions that does, inclusive, that does intervals in between, in the tails, to the left and to the right. But here you have like 8 more options because you have less inclusive and exclusive on either side. So for every interval, we have 4 variants, right? The exclusive, inclusive to the left, inclusive to the right, inclusive on both. And that just explodes the number of options and becomes a very lengthy code. So it's just easier to do it this way right now. A monitoring system records an average of 5 critical errors per day. What is the probability that between 3 and 6 inclusive? So if it's not clear what I'm asking between 3 and 6, I will tell you inclusive. So between 3 and 6. So that's very clear to us. It's Poisson and then P less than or equal and probability X between 3 and 6. And then my lambda is equal 5. And then this would be a Poisson dot CDF 6 lambda. So I'm including the area to the left of 6, including 6, minus the area to the left of 3, excluding 3, right? Because I want to include 3 in my probability. Poisson.CDF 2 lambda. Okay? This makes sense because I want to count 3 as part of my probability. If I put CDF 3 here, it's going to take out 3 with it. I don't want it. I want it to take out 2. So in other words, this is equal to probability of Poisson at 3 plus 4 plus 5 plus 6. Okay? That's the cumulative. Okay. All right, let's move on. Speed things up just a little bit. I'll do a couple of uniform distributions, then maybe if you have some questions. Okay, so the uniform distribution. And again, I'll share the notebook with you. Worry not. So the uniform distribution is a continuous probability distribution defined over an interval A and B. It's a finite interval. And once you know A and B, you automatically know what the PDF is and what the CDF is. We have the formulas in the textbook. And you actually also have the formulas to compute the probabilities, but we're going to use Python for this. Okay? Excuse me. If we want the individual density values, we call the PDF, but that's rarely the case. We're asking for probabilities with continuous distributions. It's always going to be an interval. Could be semi-infinite, so probability to the left or to the right of one value, or an interval in between, or in the tails. All right. So for this one, with the generic script, you need to replace normal with uniform. Okay, if you want to apply the generic script we developed, because that generic script was specific for the normal distribution. Okay, but for here, we're just going to have to do this by hand. If you want to use the uniform distribution in the generic script, you just have to replace normal with uniform. Okay, and it should work just out of the box. Okay, now from scipy.stats, import uniform. That should give us the uniform distribution. And let's do some questions. So now, entirely different problems. Shaft diameters are uniformly distributed between 9.95 millimeters and 10.05 millimeters. Okay, so just immediately tells you uniform distribution, gives you A and B for the uniform distribution. What is the probability that a randomly chosen shaft has diameter between 9.98 and 10.02? So this is uniform distribution, uniform, and then we are doing probability between 9.98 and then x 10.02. Doesn't matter if I put greater than equal, less than on either side, they're all equal to each other. Okay? So I'll just use the faster notation. I put exclusive. Okay? Then we can do A is equal to 9.95, and then B is 10.05, and so that defines my so that defines my uniform distribution. Okay, and then x1 is 9.98 and x2 is 10.05. So that's what I want to find the probability for. And then my probability is equal to, or I can just type it. So uniform dot CDF. So this is an example where it's just easier to define the distribution itself. So I'm going to put uniform for uniform, and then I will define it. So if you notice here, it needs two parameters, location and scale. So that's how you define the uniform distribution here. We didn't discuss this in class because we had the analytical formula, but this is how you do it in Python. In Google Sheets, it might have its own different way of defining the uniform distribution, or in your calculator, if at all available. In Python, it is available, but that's how you define it. You give it location and scale. So instead of having to put location and scale every time, I'm just going to define it once. Location is equal to A, and scale is equal to B minus A. And then I can simply say uni.cdf at x2 minus uni.cdf at x1. Okay? Did I pen 10.02? My apologies. Yep, 0.4. Now you can adapt the generic script we did if you want for it to work with the uniform distribution. In the generic script we had mu and sigma. Over here you'll have A and B, so you'll redefine the uniform distribution, replace normal with uniform. It will just work out of the box. Okay? You're welcome to do that as well. Okay, so let me see. I'll do. Well, they're kind of all the same. Thickness, sensor measurement. Okay, here's another example. A sensor's measurement error is uniformly distributed between minus 0.5 and 0.5 units. So this could be, particulate matter or some concentration. What's the probability that the absolute error, or the sensor's measurement, that the absolute error is less than 0.2? So the absolute value of the error. So that's not absolute error in the sense of numerical methods. Okay, relative, approximate error, or absolute error. So that's absolute value of the error. Okay, so you're asking what is the probability that P of the absolute value of x, okay, is less than 0.2. So that would be equal that the probability is between minus 0.2 and 0.2. Okay, so we can define our uniform distribution. I'm going to copy these, put them here. In this case, A is minus 0.5, B is 0.5, x1 is minus 0.2, and x2 is 0.2. Okay, define the uniform distribution, and then take the CDF. It's Let me see, location scale. Yep, it's the same value, right, as the problem before. How lucky. But then they ask, what is the PDF value at 0? You do uni.pdf at 0, and that gives you exactly 1. So problems repeat in this case. We'll do one more with uniform, and then we do normal. Now the normal, we can do the generic script that we used last time. Loads arrive uniformly in a 10-second maintenance window, 0 to 10 seconds. Okay? What is the probability that a load arrives between 2 and 5 seconds? Again, this is a uniform distribution problem because it's kind of given to us. Uh-huh.
Shouldn't it be 0 for a singular point of 0?
This is a PDF density. There's not, yeah, so the probability density is not 0. The probability at 0 is 0. But the PDF, remember, the PDF is not 0. That's because it's a density. So the units of this value are what? Probability per whatever error units.
Oh,
So,
because
right?
it's over 1 unit. Okay.
Yeah, but yeah, don't. So PDF is non-zero. The PDF is non-zero. The probability, if I had asked, what is the probability that the error is 0? It's 0. There's no probability at a single point. But what's the density at one point? It's non-zero. Loads arrive uniformly in 10-second maintenance window. So A is 0 and B is 10. What's the probability that a load arrives between 2 and 5 seconds? 0, 30. So yeah, 30%. Okay, 0.3. All right. So for the normal distribution, we did a lot of work with the normal distribution. Let me just check something here. So for the next problems, you can use the generic script. So let's try to do both. A couple of examples on both. So Spring Stats, exam1 review. So you're not responsible for the sampling distributions for the central limit theorem. So your exam, your material does not include CLT. So up to n, including continuous distributions and the normal distribution, uniform distribution, but no sampling of sample means, no okay, so none of those things. So we're focused on just computing probabilities given a distribution, okay? All right, so let's go after the normal distribution. We're pretty familiar with this one because it's fresh. We did this fresh last week. And if you remember, the normal distribution takes two parameters, mean and standard deviation. And from scipy.stats, import norm. Come on. OK. So we'll do a couple of problems, and we'll see if we can use our script as well. The temperature of a reactor is normally distributed with a mean value of 500 K, standard deviation of 10 K. What's the probability that the temperature exceeds 515? So they're telling us this is normal distribution. We know mu and sigma. This is P of X greater than 515. Okay, so for this, I would put mu is equal 500. Sigma is equal to 10. And then this would be 1 minus norm dot CDF of, so let's put X equal 515. Okay, so the nice thing about continuous distributions, you don't have to worry about, X minus 1, it's not discrete. Okay, so you just put the value you're looking at, location is mu, and then scale is equal to sigma, and then you get 6.7%. I want to try my generic script that we built in class. So if you remember, we did this last week. So let me import it again. Okay. I'm going to put reactor problem. And I had mu is equal to, what was it, 500? Yep, 500. Sigma is equal to 10. And then A or X is equal to 515. And then we said calculate probabilities of mu, sigma, and then X. And there you go. It's this guy. P of X greater than 500, because we didn't give B. We didn't put A and B. So it only defaulted to either probability to the left or probability to the right. We gave it one number. And so probability X greater than 515, it's this guy we care about. It's 0.0668 or 6.68. Okay? So you can use this one as well. Obviously, this one is more general, this generic script. But the problems are interesting, so, whichever one you want to use. Okay, so let's do another problem here. Pipe diameters are normally distributed with a mean value of 2 centimeters and a standard deviation 0.05 centimeter. What is the probability? A pipe diameter is between 1.95 and 2.05. So again, we can put mu is equal to, and then sigma is 0.05. Okay, and then my A is 1.95, and then B is 2.05. And then I call norm.cdf, or you can define the norm, normal distribution. Norm dist is equal to norm, whichever way you like. And you just give the properties of the normal distribution because we're going to use it twice. Mu scale is equal to sigma. And then we can just call norm dist.cdf b minus norm dist.cdf a. Okay? 6.82%. I can do, so if you have no idea what I'm doing here, you need to study. You need to go back. There's math that's backing all of this up. To reach this point of blindly using the code, okay, you need to understand what the code is trying to do. Okay, why does it do it this way? And you can trust using it. If you have no idea what's going on here, I strongly encourage you, go back to the drawing board, go back to the slides, go back to the lectures, and study those and understand how we built up to this point. Okay, I know it seems like such ancient history, but it's not. It's like 2 weeks ago we were covering normal distribution. Okay. Now you can put this in my other script, and you'll get the same results. So we can do this one, the pipe diameters. Mu is equal to, and sigma is equal 0.05, and A is 1. Actually, why am I doing this? Let me just copy and paste these. Don't you wish you can copy paste in life? All right, calculate probabilities, mu, sigma, A, B. And then that gives you the entire, all possibilities, okay, all possibilities. We are interested in only one of them, which is this one, P between 1.95 to 0.05. And that's exactly for Z value between -1 and 1. If you don't understand that these are equal, again, you have to study, because I will ask you about this. Like, I'll ask you a probability problem and tell you, oh, this is equivalent to P of Z less than and whatnot, and just try to get that information from you. It's 0.6827. We're rounding on the other one. So this is it. There's a few more problems in these notebooks. Go through them. This is the spirit of the exam. All of these, what? You have 5 probabilities, distributions, 3 questions per probability, that's 15 questions, worth 3 points each, okay? So that's a lot, almost half of your exam. So make sure you practice this. All of the problems are going to look like this. Very short, concise, get the answer. Make sure you can put 2 windows maybe next to each other on your laptop, right? Or if you want to use your calculator, make sure you practice all of these. I think it's easier, I know it seems easier in Excel or Google Sheets. I think it's easier in Python because you're more expressive, and once you do it once, you have the script ready, you just copy paste your way through this and get all of your answers, okay? All right, should we look at the Q&A real quick, or if you just have questions or you want to leave, it's up to you. Yes?
So what we did today in class is something we'll have available while we're taking our exam, or is this something we can study if we won't be?
Yes, yes. You will be able to access all of these scripts in the exam, okay? So I'll repeat again. The generic script, these 5 scripts, you are allowed to use in the exam. If you have programmed something in your calculator, use it in the exam. If you programmed an Excel sheet to do this for you, use it in the exam. But you're not allowed to use your homework notebooks or they're not going to apply anyway. But don't access your notes, your slides. The only thing you can access are these scripts, your calculator, whatever programmed in it, your Excel sheet, whatever you programmed in it, and your cheat sheet, okay? Yes?
Would you like us to be like uploading the notebook that we use for our calculations?
No, just keep it around, okay? Just keep it around. Yeah, it just adds more time and effort, and yeah. But if you're using your scratch paper, definitely keep the scratch paper as well. I'm not going to take it from you. I have enough clutter in my office, but keep it with you for what? The IRS rule, 2 years. Keep it with you for a couple of weeks until I grade the exam.